Tēnā koutou, tēnā koutou, tēnā koutou kata. Ko monga kiki te monga, ko manaka te moana, ko Ngāti Pākehā te iwi, ko kolas tauka whānau, ko Bill tauka ingoa. Tēnā koutou, welcome to Conference 201. I'm Bill Collis. I'm one of the lecturers in the course. So let's see my screen with you and we'll get started. So as you can see, I've got the lecture notes open in Word here, and we'll just go through these. This is how the lectures are going to work. You'll see in the announcements that there are other things for you to do, of course, during this course. And yeah, we'll just get on with it. So let's start at the introduction. So embedded systems. These are the really, everywhere. They're going on, doing things for us in our lives that we could never imagine, actually. So much so that the whole nature of our world relies on these computer-controlled devices nowadays. And this time in history has become known as Industry 4.0 or IoT, the Internet of Things. At the heart of embedded systems are these things called microcontrollers. This includes other digital controllers like FPGAs and ASICs and microprocessors. And embedded systems are ubiquitous. That means that they're everywhere. But the thing is that we're seldom really aware of what's going on around us and unaware of what they're doing for us. But they can actually control and regulate our lives better than we can ourselves. A washing machine measures the volume and dirtiness of clothes and determines for us the amount of water and the length of the washing cycle. Output emissions of a car are monitored, and the embedded system controls the ratio of fuel, air, and exhaust gases injected back into the engine, making decisions on our behalf about fuel consumption, efficiency, and pollution. And this course really is an introduction to microcontrollers and their programming. What I want to do is have a little chat about cash here. So cash is a device from the ASB Bank. The cash is a little plastic elephant, but it's got an embedded controller inside it, which is connected to your network at home and tells a child how much money is in their bank account. And when you want to give money to your child, for instance, a little bit of pocket money or a little bit of money to spend or save, all you do is take out your phone and flick them a bit of money and it shows up on cash to say how much is in their account. A little instance of an embedded system. In a car, for instance, we have a huge amount of embedded systems. There's 50, 100 more microcontrollers doing things inside cars for us all of the time. Let's go down to the next page. I want to talk about the learning outcomes for the course. Learning outcomes, just highlight this, and success criteria are two independent little things I want to talk about. There we go. So a learning outcome is really a big idea about a course. What are the big ideas in this course? What is this course really all about? And you can see them highlighted in yellow here. The interrelatedness of hardware and software. The fact that an embedded system is an automaton. That they are reactive and responsive. That this course is about helping you grow your understandings of what transparent software practices, high quality software is all about. About the fitness for purpose of a product and how you might choose the device to meet that fitness of purpose, and an integrated development environment, what they are. And for you to develop your understandings and work with complex tasks with multiple relationships. So these are the big ideas, and these big ideas fall in with this big idea at the top here about developing a viable mental model of what an electronic or an embedded system is. And this means that when you look at something, you don't just see it for what it appears to be, but what's going on inside it. And that's what I want you to develop as part of this course, is a viable, a usable, realistic working model in your head of what's going on inside a microcontroller-based embedded system. That's what this course is about. Now, of course, these big ideas, these learning outcomes, all relate to the word understand. But how do we know when we have understood something? And this is where this term success criteria comes in. In success criteria, these are the actual concrete things that you can do in a course and with your learning that show that you do understand the big idea. And if you want to think about this in terms of your own learning, then you can look at this success criteria and put the word I can in front of every single one of them. And at the end of the course, I would like it if you were able to put I can in front of every single one of these success criteria and say, well, I can explain this, I can describe this, I can set up, I can apply, I can list, all of these different things. And then when you can do all those things, you'll be able to say, well, actually, I now understand the big idea in this course. And if you have all these understandings, then what you've got is a viable mental model of a microcontroller-based embedded system. So that's what I really want you to take away from this course. Down the bottom of this page, I want to draw you to a piece of educational theory. And I think, why would I share educational theory with you? Well, this is all about you understanding what it means to learn. And so that's why I think as an educator, it's really important for you to understand the learning process. And I'm going to talk about something called the solo taxonomy. It comes from a guy named Biggs. And he says that when you're looking at the outcome of learning, what does the student exhibit in terms of their outcome of learning? Are they pre-structural, which means that the question you're asking them to do is too big for them? They have no concept of what has been asked of them. Do they have a unistructural idea? In other words, are they able to answer certain facts about a course or carry out a certain calculation using a given formula? Well, that's not really good enough either. The next two levels are the most important ones for this course, and that is multistructural. Now, in multistructural, what that means is that you're able to piece together information from different parts of the course and understand and interpret them accurately. It's really important. And of course, the slightly bigger thing is this relational understanding. What I want you to go away from in this course is having a relational understanding of these different things so that you can think, well, if I do this, I'll get this effect. And if I do this, I'll get this effect. So how do I find the balance in between them to actually make sense of my knowledge and solving a problem for someone? The extended abstract level is where you're able to take the information and put it into a new context. That is not the goal of this particular course. That, of course, is the goal of a design-based course, or in actual fact, what you do in work. When you're out there in industry and you're asked by your boss to do something, you think, oh, well, no one ever showed me the formula for that, or no one ever told me that in university. Well, it's not like that, because what you have to do is actually take the knowledge you have and use it in a new context. And so that's what you would do in a design-based course and in industry. So what I'm going to focus on mostly is this multi-structural and relational understandings, not giving you a few isolated facts. And certainly I'm not going to ask you to do things which I haven't prepared you for. So let's get into it. The Atmel and AVR range of 8-bit microcontrollers. Now, Atmel, which is now owned by Microchip, is one of many brands of microcontrollers, Texas, Renaissance, NXP. There's a great many of them. And as it is, the Atmel brand includes many different ranges of microcontrollers. The AVR8 is one of those, and that's the one that we'll focus on. Now, the AVR8 actually comes in subtypes, the tiny, the mega, the X mega, the 90, and it's the 80 mega that we're going to look at. You know, Atmel produces, well, it's a slightly old fact, but probably around about 40% of the world market share of 8-bit microcontrollers. So that's about 2 billion per year, sold at an average cost of around 30 cents each. This is a big industry. There's a lot of these things happening and going on. Each subtype of the AT, tiny, mega, X mega, has many different variants. And we're going to be looking at the AT mega 328p in detail. And of course, once you understand the AT mega 328p, you'll understand the AT mega, you will understand the AVR8, and that will give you a big clue as to what happens inside most other microcontrollers. And that's why the mega 328p is chosen for this course. It's not too difficult, but it is complex enough, that's for sure. Now, you'll often start with a development kit when you're working with a microcontroller, and that's a little board like this, this explained mini board, or for instance, this is the Arduino Nano board. These are what we might call development boards. And inside or on the board, you'll find that there's a microcontroller. And a microcontroller looks like a little black insect with lots of legs. And this little black cover can be peeled away to show you that what's inside is like a city block. Really, it's just a fascinating electronic, millions and millions of devices inside this molded, built up on top of one piece of silicon. In fact, if you go to zeptobars.com, you'll find that some really fascinating high resolution pictures of microcontrollers and microprocessors that they boiled away the outer plastic, and so you can see what's going on inside them. Now, what we're going to look at in this course is the Atmel AVR. So what is inside one of these devices? There's a CPU, a central processing unit. We're going to be interested in this SRAM, the static RAM. The flash, now this is where the memory of the programs. So when you write a program, it's converted into code and then put inside the flash. And the microcontroller runs the program from the flash. There are I/O, input-output ports, and we're going to look at some timers, so timer counter 0, timer counter 1, timer counter 2. We're going to look at the analog to digital converter with its associated internal reference. We're going to look at external interrupts, and we're going to look at the USART, which is the serial communications part of the microcontroller. So this is what we're going to look at during the course. So what is a computer or microprocessor or microcontroller? Well, actually, computers have microprocessors. A microcontroller is a single computer in one IC, integrated circuit or chip. It contains this CPU and an arithmetic logic unit. So you've learned a little bit about this in the other part of the course, the fact that there is a way of doing addition and subtraction and how we might do a shift left and a shift right using shift registers. So those are the sort of things that are built into this ALU. So it's a fairly complex block of logic. The other things inside the microcontroller is, of course, the flash, which contains your program. There's the EEPROM, electrically erasable programmable read-only memory, which is where you can store data that you want it to be maintained when the power is turned off. Of course, the flash, the program, is maintained when the power is turned off to this device. The EEPROM, the memory that you put in there, the data you put into this memory is retained when the power is turned off. But over here we have the static RAM, RAM standing for random access memory. So what this means is that it's only stored for as long as the power is turned on. We use a word volatile to describe this, as opposed to the flash and the EEPROM, which are non-volatile. We also have a bunch of hardware registers, and we have some general purpose registers. So there's a lot of registers and a lot of register transfers going on to do calculations. You need to know a couple of really important things: that your programs that you write in C are not stored in the microcontroller. They are compiled into machine code, and that is stored in the flash. For instance, here I've taken a little program. Here's a program up here. Very simple. All it's doing is adding two numbers together and storing it into a variable called C. What this looks like when it's put inside the microcontroller is it turns into a range of, let's just zoom this a bit, range of machine code numbers which are stored sequentially in flash: 83E6, 80930301. And you can see this file that what I've done and looking at here is the .lss file, and you can find this when you compile a program in Atmel Studio. Just open up the LSS file and it will help you understand exactly what your C program has become in terms of machine code. So you can see, first of all, A equals 99. What that means, the 83E6 means load register 24 with hexadecimal 63, which of course is the decimal 99. So over here we have our registers, and we're going to put into 24, we're going to put the number 0x63. Now, what happens then is we store what is in register 24 into a location in RAM. So down here is our RAM, and we're going to store the number that is in register 24 into the RAM. And so this is A equals 99. So what it's made up of is the number 99 is stored in a register, then that register value is copied into RAM. And we do the same with B equals 4. We use the same register, and then we store it though in a different memory location. We're going to store it in 0, 1, 0, 2. Now, down at the next one, C equals A plus B, first of all, what we're going to do is we're going to take the number that's in one memory location, which is 0, 1, 0, 3, which is our variable A, and we're going to store it into register 18, which is one of our general purpose registers. And then what we're going to do is we're going to take the number which is stored in 0, 1, 0, 2, which is memory B, and stick that into another register location. We're going to take 0 and store it into another register location. And you can imagine that what happens when you add two 8-bit numbers together is that you can get something larger than an 8-bit number as a solution. And so what it's doing there is it's preempting the idea that there's going to be a number larger than 8 bits and giving you another register to store the overflow into. So this is how the compiler works. And then it goes through and it does the addition, and it does the addition with carry. And then finally what it does is it stores the number into the memory location 0, 1, 0, 1 and 0, 1, 0, 0. So this is how it works. And you'll notice that it did a 2-byte addition because I said to it to store a 16-bit number. Okay, so that's a simple overview of what happens inside a microcontroller. I'm not going to ask you to repeat this sort of process, but I need you to understand that what is happening is that your C program is not stored in the microcontroller. It is compiled into machine code, and the machine code is stored in flash. The CPU fetches these instructions, follows them out, puts a number in a register, puts another number in a register, adds them together, takes the solution from that up third register and pokes it into somewhere else in memory. So this is the general sort of flow. And you just need to understand that this happens. It's really important that you have this good picture in your mind of this sort of thing happening. Now, one of the things that's important in this course is the difference between an FPGA and a microcontroller. Now, you've done a little bit of work with FPGAs. And so an FPGA is a collection of hard logic blocks, which are inside a single package. Now, when you write VHDL or you do your schematic capture in whichever software program you're going to use for that, Altium, for instance, and then what it does is it actually rewires the inside of the block so that the FPGA becomes something, and it becomes a circuit. Now that's quite different to a microcontroller. We'll see that shortly. Now this sort of functionality where we're wiring logic blocks together allows us to do things that can be done in parallel. Now a microcontroller is not like that. You've got this complex block of hardware which exists. You don't change its structure at all like you do with VHDL or your schematic capture. What happens is that you write a program which is a sequence of instructions, and these are compiled in machine code, as I've already explained, and then they're stored in hex files, and this is written into the microcontroller's program. In this way, these programs tell the fixed hardware of a microcontroller what it will do. So you see, there's a big fundamental difference between an FPGA and a microcontroller. The coding that you write for an FPGA tells it what to become. And inherently, you can make it parallel in nature. But in a microcontroller, your sequence of commands tell the microcontroller what it will do. And that means that these operations are carried out sequentially, not in parallel. In fact, if they're carried out fast enough sequentially, then they won't actually appear to be sequential, but will appear that they could be happening in parallel. But it's really not something that happens. It's just they are carried out sequentially. Now, as part of this course, I did ask you to review your notes on C. And so that's just that reminder there. I want to look at the Arduino Nano development board itself. So it's a tiny little board. It's got these the microcontroller, a reset switch. I've done another video explaining all of these. What I really want you to take note of is not the numbers that are printed on this board. because that's set up to run with the Arduino software. But these port D1, port D0, PC6, these numbers here and down here, they're the ones that we're going to refer to in this course. And we're going to look at these in terms of ports. Now, a port typically has 8 bits. And so on our microcontroller, you can see up here, I've got port D, port C, port B, I've got port B, port C. Yep, that's what I've got. What I've got is I've got port B, port C, and port D. And these have connected to them either input or output devices, and IP, input, OP, output, input transducers, output transducers. And we also use the word sensors and actuators to refer to these. Now, each port typically has 8 pins, and they're numbered from 7 to 0. And the thing is, though, that we don't have access to all of those on this board. In fact, in this particular microcontroller, not all of them are available to us at all. So what we'll find is that port B has pin 5, 4, 3, 2, 1, and 0, but it doesn't have 6 and 7. The same with port C. It doesn't have bit 7 and 6. It only has 5 down to 0. And port D does in actual fact have 7 down to 0. So this allows us to connect this many number of I/O devices to our microcontroller. And the next most important thing that you need to do is you need to have access to this data sheet. That's a critical part of the course. A lot of work will be done in reference to the data sheet for the ATmega. Now, it's not something you want to print hundreds of pages long. We'll refer to the certain sections and I'll go through different things. So that's as much as I want to take in this introductory video, and I hope you're going to enjoy this course and build this into perspective with the fact you're working on an assignment. And I've also made available the practorials for you to look at and work through. Now, if you don't have the hardware for the practorials, that's fine. You can still work through them and have a look at the videos I've made. They're a really important part of your learning. We'll see you later. Bye.